Thank you very much for introducing me, and really appreciate for giving me an opportunity to talk about my activity. Today, I try to talk in English. Sorry for my poor English, and thank you for your patience in advance. This time, I would like to show my design of RISC-V CPU core. It has enough specification for MCU, so I think it can be adopted for practical commercial devices, or of course for prototypes for some R&Ds and educations. Beforehand, let me introduce myself briefly. My name is Munetomo Maruyama. I have 3 identities. First is a hobbyist. My first touch to microprocessor was 8080 when I was 16 years old. After the encounter, I have been losing myself in making board computers, logic designs, and coding programs for 43 years. Second is a professional engineer. I have developed microcontrollers, microprocessors, SoCs, and mixed signal devices for around 35 years. Still, I engage in product development in a semiconductor company. Third is a freelance technical writer. I have been writing around 100 articles of electronics magazines and around 10 books about MCU and FPGA for 20 years. Today's presentation is an activity as a hobbyist. This is today's agenda. I will talk about RISC-V impact and specification of the core, designs, actual works, and summary. Maybe all you already know about it, but I want to review RISC-V impact again here. As for conventional popular CPU core, such as ARM, there are very comprehensive ecosystem surrounding proven core logic IPs. They make large culture and big society. Also, these are very reliable and have many achievements. But the core IP logics require very expensive license fees and permanent royalty fees. These fees may be annoying matter for ROI of some kind of low-cost products. On the other hand, there may be cases to design self-made original CPU core to avoid such expensive fees or to realize original dedicated features. In this case, ecosystems such as compiler, debugger, middleware, and these are very poor or nothing. And if we try to prepare them, we need huge human resources and expensive costs to develop them. So this case is often not practical. And this is my understanding of RISC-V essential. Today, there are already comprehensive ecosystem based on common instruction set architecture and related specifications. But position of CPU core logic at center of this figure is completely open, and anybody can design it. I believe this style has big impact to microprocessor and microcontroller designers. Once we design self-made RISC-V core logics, we can get comprehensive ecosystem, and we need not to pay any license fees and royalty fees to CPU vendors anymore. This means we are happy. It must be a kind of big paradigm shift in CPU IP world, I believe. Based on this background, I decided to design a RISC-V CPU core by myself. The reasons and motivations are divided into two categories. First category is as my public stance, to have practical CPU core, to get large ecosystem world, to have a white box CPU that can be improved by myself, and so on. And second category is as my real motive. Why self-made? Because to enjoy. That's all. This is my real intention. Okay, next chapter. I will show you the spec of my design CPU core. Target products and application of the CPU core. The target is ASSP microcontrollers for industrial and consumer applications. Those are some kinds of feedback control system, such as motor controls, power converter controls. These applications require fast multiply and accumulation in both fixed point and floating point operations to calculate digital filters. In general, for such embedded applications, 32-bit number, 32-bit is enough for both integer and floating point to calculate the digital filter. From the target application, I decided ISA as RV32IMAFC. For digital filter operations, multiply and divide division category M and floating point category F are required. In both integer and floating point instructions, addition, subtraction, multiplication, and multiply and addition should be executed in one cycle. And non-volatile memory, such as flash, occupies a major area in MCU die. To reduce cost, reduction of memory size is important. Therefore, complex code category C is necessary for MCU. And more, in general, embedded MCU want to use low operating frequency to reduce power consumption. For electric circuit control, such as power converter, the sampling frequency of feedback control is often over 2 MHz. If the CPU operates in 100 MHz, there are only 50 clock cycles in sampling period. So task switching using interrupts in one CPU core does not have enough performance because save and load 32 registers consume many clock cycles. High-performance control systems tend to avoid using interrupts for task switching. To make it, the system is divided into small blocks, and one CPU engages in controlling each small block with tightly coupled AD converter and PWM timer. Therefore, multi-core or domain-specific architecture is preferred, which uses shared memory among multiple cores. Even in low-end MCU, category A, atomic, becomes important ISA. The spec of a self-made RISC-V core is shown here. Core name is RISC-1. stands for much more RISC. The supported heart counts 1 to 1 million. All hearts can debug from common JTAG debugger. If you want to implement 1 million hertz in one die, please use TSMC picometer process if available. The MCU is controlled by a fixed firmware stored in non-volatile memory. All zones in the MCU are secured, and program codes always run in machine mode. So privilege mode is the only machine mode. To make the CPU core practical one, debug support is very important. So I implemented full functional debugger block with hardware trigger function based on the debugger spec version 0.13.2. Instructions shown here are implemented. Base integer, CSR access, multiplication and division, atomic, compressed, and single precision floating point are fully implemented. And control and status register and other register resources shown here are supported. Machine mode CSR, floating point CSR, interrupt control CSR, debug and trigger CSR are implemented, and M time for generating periodic interrupt is supported as a memory mapped peripheral, and data aggregated registers are implemented for debugger. Interrupts and exceptions required for MCU are fully supported. In addition to standard RISC-V interrupts, 64 IRQ inputs are supported. They can configure 16 level priorities among them, and sensing mode can be selected from level sense or edge sense. To control 64 IRQ, a dedicated interrupt controller is implemented. And of course, E-break, C-break, E-call, etc. are implemented as synchronous exceptions. This table shows all asynchronous interrupts and synchronous exceptions supported in this core. In this part, I explain internal pipeline structure and block diagram of CPU core briefly. This slide shows CPU pipeline structure. Integer pipelines have 3 stages to 5 stages. Register forwarding, and pipeline store controls are implemented as usual CPU design. Integer division and remainder instruction use non-restoring method and take several clocks to complete. And conditional branch, that is whether taken or not taken. In D stage, the D stage needs register forwarding from E stage or write back stage to judge taken or not taken. This slide shows FPU pipeline structure. FPU pipeline is independent from CPU. If there are no register conflict between CPU and FPU, each pipeline can go on in parallel. FPU pipeline consists of combination of multiple stages. Stage I converts 32-bit IEEE format to internal format with long bit length. Stage A executes addition and subtraction using the internal format, and stage M executes multiplication, and stage F converts internal format to 32-bit IEEE format with rounding operation. And F add and F sub, addition and subtract, have stages I, A, and F, and multiplication, F mal, has I, M, and F stages. And multiply and add, F, M, add, has I, M, A, and F stages for each. These instructions can be executed contiguously without stores if no register conflicts and no resource conflicts. Division and square root use Gold-Schmidt algorithm, so each pipeline consists of I and a combination of multiple A and M and final F stage. The reason why the long length internal format is prepared is to keep accuracy during Gold-Schmidt operation with multiple additions and multiplications. And the convergence loop counts in the algorithm can be configured by dedicated CSR if you want to change execution cycles and accuracy. You can change the convergence loop of the algorithm. This is a block diagram of the core. It consists of instruction fetch unit, pipeline unit, data path unit, floating point unit, and debug support unit. Instruction paths and data paths are separated as Harvard architecture and LRSC, load reserves and store conditional monitor bus, watches reserves address liveness. Debugger can access the path by both abstract command and system bus access command. In this section, I will show my detailed works in this project. For this design, I worked only weekend due to my former jobs in my company. And I started this project in 2017, but suspended for 2 years due to another personal project, and restarted from 2020, at last finished in this year. I have spent about total 2 years to design. My design progress history. In early phase, I designed the debug transport module with JTAG interface. In this design, I checked connection between OpenOCD and FPGA. Of course, OpenOCD reported errors due to no main debug module implemented, but at least I could check connection to JTAG tap controller and access to JTAG tap registers. Such connection check in early stage is very important because most troubles occur in such interfaces. After design HTTP bus matrix, I have completed debug block and checked bus access from OpenOCD using FPGA system. After that, I have built most of integer ISA, CSR blocks, and remained debugger blocks such as trigger unit. Integer division instruction use this non-restoring method. So I have verified the algorithm using C model and converted to RTL code. After completing ISA, except for floating point, I wrote and verified floating point operation model in C code, and I have converted it to RTL and verified all. This is my development environment, almost free. Platform is Ubuntu Linux. Logic Simulator is a free version of Model Sim, which is included in Intel Cortex Prime Lite Edition. The free version of Model Sim says it has limitation of RTL line counts, but if simulating logics that have only pure standard RTL statements and there are no FPGA specific IP such as IO, PLL, program, and logic primitives, it seems there are no limitation, even in the free version of Model Sim. Very comfortable to use for me. And software development tools is Eclipse and GNU toolchains and OpenCD. All these are completely free. FPGA board I'm using is low-cost classic D10 Lite with Intel Max 10 on it. It costs only $95. Tooling for FPGA is Cortex Prime Lite Edition, free version. And USB to JTAG interface is popular ARM USB OCD from Olimex, but I made almost compatible one by using FTDI chip. Using breaker boards of FTDI chip, breadboard, and some wiring, I made USB to JTAG interface less than only $20. This is a block diagram of simple SoC with a CPU core. I have used this system for both logic simulation platform and FPGA implementation. Here, the verification methods used in this project. First is a very simple vector simulation. CPU fetches instruction code from RAM block initialized by binary code built by a C compiler. Second, applying a random weight cycle in instruction access and data access during the above vector simulation. Third, applying bus conflicts among multiple hearts during the vector simulation. And number 4 and number 5 are the verification of C model for integer division and floating point algorithm. Input data for verification are applied as many as possible. 6. Verified using RISC-V arc test for RV32IMAFC instructions as RISC-V compliance test. 7. Verified using RISC-V tests, including atomic and floating point, as additional RISC-V compliance test. The last is to run several applications, including auto spotting and benchmarks as system level verification. This is a result of FPGA implementation. Without floating point ISA, 20 MHz operation is okay, whereas with floating point ISA, it becomes 16 MHz due to interconnect congestion in low-end FPGA, max 10. And this sheet shows sample programs provided. Basic prototype samples for CPU and FPU supporting interrupt handler, UART, printf, and other IOs. And free RTOS porting, and Drystone benchmark, and CoreMark benchmark. All programs are provided as Eclipse projects. Finally, let me summarize this session. These are what I have done in this project as described here. And today, I have pushed all resources on GitHub and set it public as open source IP. The URL is shown here. You can download all resources from this URL. And this is a roadmap of RISC series I will engage in development continuously. And there are still many to-do items, but all are very interesting work for me. I will continue to these developments. And this is my last slide. According to information on the RISC-V international site, there are over 100 RISC-V cores in the world. Recently, RISC-V commercial IP are growing rapidly, and many of them support floating point and atomic. I think such a situation is very good for RISC-V to expand its culture and ecosystem. I heard that most of commercial RISC-V IPs have reasonable license fee and royalty fee, but maybe not zero. On the other hand, free IP still occupy a large 44% portion of all cores, but free cores which support floating point and atomic core are minor yet. I want to say more free IP. Even in the free IP, competitions among IPs are also meaningful to grow each other. My designed IP is still a baby and needs to brush up more. Maybe there might be bugs, so I will make my efforts continuously. Let's design and release our free RISC-V IP more, then the wonderful culture and ecosystem in RISC-V system is waiting for us. Thank you very much.
Thank you very much. I'm waiting question. So please submit on Slack. I have a dream. Talented student will learn from you. by using the EDA tool in the Linux, RISC-V ecosystem and create FPGA, so students can also simulate, debug, and estimate performance. So students can run real software on the FPGAs. So thank you for your contribution to the book and articles, and also this time GitHub. So I think I hope many students will do like you.
Yeah, I hope so. I hope so very much.
Yeah.
Thank you very much.
Also, okay. One question from the audience: how many LUT consume the default disk 1 configuration?
Okay. I show you the slide of the FPGA result. This one.
By the way, I like your core name much more. Disk, yeah, it's great name.
The lookup tables, consume of the lookup tables may be shown here. So this FPGA has about 50K lookup table, 50K slices. So if I implement without floating, it consumed 46% of this FPGA. So maybe less than half of this FPGA. This FPGA has a logic element about 50,000, and it consumes about 23,000. But if we implement a floating point, it consumes 84% of this FPGA. Okay.
Does it have 1 million hearts?
Pardon?
Sorry, does it have 1 million thread or heart?
Heart counts?
Yes,
About heart count?
Yeah.
Half count. Yes. Architecturally, this core supports 1 million hearts. That's parameterized. You can parameterize the half counts. Only change the defined statements. But really, but 1 million half counts are not realistic. But you can simulate.
I see.
Yeah.
Okay, yeah, that makes sense.
But maybe actually in MCU, maybe 4 or 6 cores are required actually, so that it has meaning for the multiple hearts in MCU.
Yeah, thank you for your presentation and contribution.